Hello, our viewers. On our previous discussion under rotational motion or angular motion, we have tried to discuss about how to determine the total kinetic energy of rolling bodies. So the total kinetic energy of rolling body is the sum total of the kinetic energy, translational kinetic energy due to its center of mass, and the rotational kinetic energy. And we have also tried to see how to determine the speed of a rolling body if it is released from the top of an inclined plane and reached at the bottom like this. It's possible to determine its speed. Since this object is a rolling body, its kinetic energy at the bottom is the sum total of rotational kinetic energy and translational kinetic energy. And we have found this expression that the velocity v is equals to root of twice of mgh r squared over mr squared plus I. In this case, where I is the moment of inertia. So that the speed varies due to the change of the moment of inertia. Therefore, the speed or the velocity of the rolling object, is related inversely with that of the moment of inertia. So this was what we have seen previously. And at last, I have gave you, if there are three objects like a ring or a hoop, the cylinder and a sphere, if these bodies are made of the same material, having the same or equal mass and equal radius, if they are released from an inclined plane of height h equally, among these objects, which one reaches to the bottom? You have to put it in precedence. So I have gave you this question. I hope you have tried to answer this. Actually, you should have to compare the moment of inertia of those bodies to determine their speed. Actually, it's related with that of a speed. We have already determined the equation. So let's see. Here you have the speed. To determine the speed, twice of mgh r squared over mr squared. All the three bodies, the ring, the hoop, the sphere, and the disk, all have the same mass, all have the same radius, and all are released from the same height. The only difference is that their moment of inertia. We have already determined this equation. So we should have to compare their moment of inertia. Therefore, the moment of inertia of the hoop or a ring is mr squared. The moment of inertia of a disk or solid cylinder is given to be 1 over 2 mr squared. And the moment of inertia of a sphere is given to be 2 over 5 mr squared. This one, half mr squared, and 2 over 5 mr squared. Therefore, we should have to compare the moment of inertia of those bodies. Therefore, the moment of inertia of the ring or hoop is mr squared. The moment of inertia of the sphere is 2 over 5 mr squared. The moment of inertia of disk is 1 over 2 mr squared. So when you compare this moment of inertia, this is 1 times mr squared. And this is 2 over 5 is 0.4 mr squared. And 1 over 2 is 0.5 mr squared. Therefore, the moment of inertia of a hoop is larger than the moment of inertia of a disk, larger than the moment of inertia of sphere. Therefore, among these, the moment of inertia of a sphere is smaller than the disk, than the ring. Therefore, the smaller the moment of inertia, the larger the speed or the velocity. Therefore, which one reaches to the bottom first? So the sphere reaches to the bottom first, because from the above equation, we have found that speed v is equals to or inversely related to that of the moment of inertia. As the moment of inertia is higher, in this case, the ring has a higher moment of inertia, so it comes to the bottom lately. The moment of inertia of a sphere is smaller. This is 1, this is 0.4, and this is 0.5. So the smaller moment of inertia is for a sphere. The smaller the moment of inertia, the higher the speed, so it comes first. So when you put your answer, first the speed of sphere is greater than the speed of the disk. Then at last the speed of the hoop or the ring. So which one comes first? The sphere, then the disk, then the ring. So this was what I gave you previously. I hope you have found this answer correctly. So students, let's proceed today. Let's try to discuss about the angular momentum, the concept of angular momentum. So what does it mean by momentum? Before trying to discuss about angular momentum, what do you mean by momentum? Well, momentum is among the property of massive bodies. It is one, like mass is the property of matter or massive bodies. Inertia is a property of massive bodies, and so on. Therefore, momentum is a property of massive bodies which tells us about how a given matter exerts onto the other massive bodies due to an impact, due to collision. Okay? Therefore, momentum is a vector quantity. Actually, you have learned this concept in Unit 4 under the concept of dynamics. There is a linear momentum for translational bodies, for objects moving translationally. For example, if you take this box, it's moving on a horizontal level or translational or a linear motion. There is a linear momentum known to be P. So P or linear momentum is m times v. V is the velocity. Due to the velocity, the momentum is also a vector quantity. But in this case, we are trying to see the angular momentum or the momentum of rotating bodies. Suppose here you have an object or a point mass. This mass has its own mass, m, and it can rotate around a given axis. So while it moves, it has its own tangential velocity, v. For example, if you try to observe it from top, it is perfect circular. So here we have the mass. The mass has a tangential velocity, v. And this particle has its own mass, m. And it is at r distance from the center. Therefore, m times v gives us the momentum. Momentum P is m times v, the linear momentum. This is the linear momentum. Therefore, the linear momentum and the moment arm, as these two correlate together, it gives us angular momentum. Let's see the expression here. So here we have the angular momentum. Angular momentum is symbolized by small capital letter L, and it's given as R cross P, where R is the moment arm and P is a linear momentum. Therefore, it's possible to have this using a vector or a unit vector notation form, as R might be expressed as Rx in the I, Ry in the J, Rz in the K. It's a vector quantity. It can be represented using a unit vector notation form. Momentum is also a vector quantity. It's possible to have Px, the momentum along x, the momentum along y, the momentum along z. Actually, this means the mass remains the same, but the velocity might have a component. The velocity along x, Vx in the I, plus the mass remains again the same, m, the velocity along y in the j, plus m, the velocity along z. Mass has no component since it's a scalar quantity. The only quantity is due to the velocity. Velocity is a vector quantity, so that it has its component along each direction. Therefore, it's possible to use matrix so that you can determine the angular momentum. And the other point is it's possible to determine its magnitude. For a cross product, the magnitude is determined as the magnitude of this quantity, which is a linear momentum, the magnitude of the moment arm, displacement, sine theta, where theta is the angle between the velocity or the momentum and the moment arm or displacement. So this is how we determine the magnitude of angular momentum. And the SI units might be determined as what? The SI unit of angular momentum is the SI unit of mass, since P is mass times velocity, momentum, mass times velocity, the SI unit of mass, the SI unit of velocity, and the SI unit of momentum. Kilogram, meter per second, and meter, actually. So, kilogram meter per second, means meter squared over second. It's also possible to correlate this using Newton meter second, because it's possible to multiply this like kilogram meter squared over second. Here you can have this expression, you can multiply with this with 1, meaning S over S gives us 1. Therefore, when you multiply this one, it's possible to have kilogram, let's put only one mass, m, second times second gives us second squared. And here you have 1 second. Therefore, kilogram meter second squared, meter second. Kilogram meter second squared is Newton. Therefore, it's possible to have Newton meter second. Sometimes, it's also possible to use the unit or the SI unit of angular momentum as Newton meter second, or it's possible to have kilogram meter squared per second. In this case, momentum is m times v times r. If theta is 90 degree, it's possible to substitute sine 90 and to have a relation, such a relation, which is mass velocity times r. It's possible to determine its magnitude. Now let's proceed. The other point is it's possible to represent using angular variables or angular parameters. What are those angular parameters? Previously we have said that mass times r times v, but we know that the velocity v can be expressed using angular velocity as r times omega. So it's possible to substitute on the velocity v as what? Mass times r. Instead of the linear velocity, it's possible to substitute r times the angular velocity. So when r is multiplied, it gives us mr squared times omega. Students, I hope you do remember this concept. The summation of mr squared is known to be, it gives us the moment of inertia. Exactly. So the angular momentum gives us moment of inertia I times the angular velocity. So it's possible to express using the angular variables. So far you have seen angular momentum can be expressed using a vector form as L equals to R cross the linear momentum. It's also possible to express it using L is equals to mr times v. And again, it's also possible to express angular momentum as the moment of inertia times angular velocity. So let's proceed again. Here you have the other term, which is known to be angular impulse. It's all the same as that of a linear impulse. I hope in your linear momentum concept you have learned about impulse. Impulse is a measure of change of momentum. Okay, change of momentum. Suppose you have a given massive body moving with a velocity v. If it moves with a constant velocity v, the momentum remains the same or constant. But after a while, after a certain time t, let's call it to be delta t, this momentum, this speed might be changed. The initial speed, let it be the initial speed, might be changed to that of the final velocity. If this velocity changes, you know that from your kinematics concept, v final is equals to v initial plus a times change in t, or a times t. So let's proceed here. V final minus v initial is equals to acceleration a times change in t. This object has its own mass. Let's try to multiply both sides by mass. If you multiply both sides by mass, this one as well as this one, this gives us mass times the final velocity minus mass times the initial velocity is equals to mass times acceleration times change in t. Look here. Mass times velocity is momentum. So this is the final momentum. This is a linear momentum. Minus the initial momentum is equals to mass times acceleration gives us net force on a given object. Net force times change in t. Look here. Whenever there is a change of momentum, due to the exertion of external force, there will be a change of momentum. And that change of momentum is known to be impulse. Change of p is termed as j, which is known to be impulse. So impulse can be defined as the measure of change of momentum, or impulse can be defined as what? Net force times change in t. So this is what we call a linear impulse. Linear impulse. What do you mean by angular impulse? So for a given rotating object, this is all true. But for a given rotating object, you should have to multiply both sides by r, radius. Since a given object has a radius r, and tend to rotate on a given object. Therefore, it's possible to multiply both sides by r. Therefore, mv final minus mv initial is equals to net force F times change in t. This was the expression for a linear momentum. If you multiply both sides by this radius r, you can find that mv final times r minus mv initial times r is equals to what? F times r. What do you mean by force times r? Students, what do you mean by force times r? Well, force times r is torque. This gives us torque tau, times change in t. M times v times r, we have previously defined it as the angular momentum. Angular momentum final minus angular momentum initial gives us torque tau times change in t. So the change of angular momentum is known to be impulse. Like that of the change of linear momentum is known to be impulse. But the difference is this one is known to be angular impulse. So that to differentiate it from linear impulse, we have theta here. So angular impulse is a measure of change of angular momentum. This is a very important concept. Actually, it's most applicable. And let's try to see about the law of conservation of angular momentum. Actually, you have learned that the law of conservation of linear momentum is practicable whenever there is the external force exerted on it is 0. When net external force is 0, when this quantity is 0, it's possible to say that the linear momentum final minus the linear momentum initial is equals to 0. Meaning, when you translate this one, the final angular momentum is equals to the initial angular momentum. So therefore, in your linear momentum concept, you have learned that momentum is conserved whenever there is 0 external force applied on it. Whenever there is no force exerted, the linear momentum is conserved. The same is true for angular momentum. What would happen to the angular momentum if there is a net torque? Well, the net torque, if there is a net torque, the angular momentum changes. But in this case, if the torque is 0, net torque exerted on a given rotating body is 0, the angular momentum remains constant. Meaning, if this is 0, it's possible to say that L final minus L initial is 0. When you translate this, L final is the same as L initial. So this is what we call angular momentum. Angular impulse, Angular impulse, J theta, is a measure of the change in angular momentum of a rotating body. Therefore, angular momentum can be given as change in L final minus L initial, and torque tau times change in t. But whenever this torque tau is 0, there is a law of conservation of angular momentum. So conservation of angular momentum tells us that the total angular momentum of a system is constant. Okay, constant both in magnitude and direction if the resultant external torque is what? Is 0. So if torque is 0 on a given system, therefore angular momentum remains constant. And angular momentum can be expressed using a linear quantities and using angular quantities. It's possible to express it using angular quantities like I and omega. It's also possible to express it using mr times v. So it's possible to express angular momentum as mrv or angular momentum as I times omega. Therefore, if angular momentum is conserved, if there is no torque exerted on a given object, let's take a skater here. The skater is tending to rotate in one direction. It might spin faster or it might spin slower. Whatsoever the case, one quantity remains the same, and that quantity is angular momentum. Whenever there is no external torque exerted on her, for example, if there is no external torque exerted, the initial angular momentum, whether she speeds up or slows down, the angular momentum remains the same. In this case, the initial angular momentum and the final angular momentum remains constant from the law of conservation of angular momentum. And it's possible to express it using I initial omega initial E must be the same as that of I final, the moment of inertia final, angular speed final, or angular velocity final. So when you take these two, for example, in this case, she stretched her hands. While she stretched her hands, the moment of inertia increased. The moment of inertia is a measure of distribution of mass from a given axis. So while she stretched her hands, the mass on her hands is far away from the axis of rotation. Here we have the axis of rotation. So her hands are stretched so that the moment of inertia increased. I increased. While she collapsed her hands and brought it nearer to the axis, the moment of inertia decreased. In this case, the moment of inertia is smaller. But in this case, while she stretched her hands, the moment of inertia increased. But in both cases, the angular momentum remains constant, since there is no torque exerted. Therefore, if the angular momentum remains constant, if the moment of inertia is increased, the angular velocity must decrease, so that it counterbalances the angular momentum. Therefore, in this case, we have a smaller moment of inertia, meaning a higher angular speed, so that she spins faster. Okay, in this case we have a smaller moment of inertia. Why smaller moment of inertia? Because she compressed, or she collapsed her hands and brought it nearer to the axis of rotation. Therefore, in this case we have a smaller moment of inertia, but a higher angular velocity. While she stretched her hands, the angular momentum increased. Because radius increase. Actually, the mass remains the same, but r increase. So that moment of inertia is the sum of mr squared. Therefore, those particles on her hands increase due to the radius r. Therefore, the moment of inertia increase. While the moment of inertia increase, the angular speed decrease. Therefore, I hope you have seen such phenomena in your movies, in different movies. So whenever someone spins, while they are collapsing their hands, they are spinning or moving faster. While they straight their hands, they are moving slower. So this is the physics concept. This is a concept. Therefore, keep this point in your mind. The moment of inertia remains constant, but it's possible to increase the moment of, the angular momentum remains constant, but the moment of inertia might increase and decrease. So keep this in your mind. This is also true. The same concept appears here. While he stretches his hands, the moment of inertia increase. So that's the moment of inertia. While the moment of inertia increase, the angular speed decrease, the angular velocity decrease. While collapse and brought nearer to the axis of rotation, he spins faster or moves faster. Okay, so this is the concept. Now let's try to solve one good example. And this example appears on your national exam, actually. So let's try to see, let's try to solve it together, or let me give you a minute, then you will try to solve it together. So students, I hope you have tried this problem. Let's try to solve it together. Suppose here you do have a planet of mass m and circulating around a given star. Actually, planets or comets and so on, they do have elliptical orbits around a given parental star, so that it has elliptical orbits. If its velocity at a given point A is 60,000 meters per second, and if the radius at B is 8 times Ra, what is the velocity at point B? Here we have the figure. Here we have a planet, okay? And this planet tends to rotate on this elliptical orbit. Here you do have the star. Actually, here you have the star. Therefore, at some point in the elliptical orbit, there is a smaller radius. Let's call it to be Ra. And at some point here, you have a larger radius, Rb. Rb is given to be 8 times that of Ra. 8 times that of Ra. So this planet tends to rotate and reach here. somewhere here. So the question says that the speed of the planet at this point is, the velocity at point A is 60,000 meter per second. So what is the speed of this planet while it reaches at this point B? What is the velocity at point B? Okay, at point B. So a very important equation to correlate this is the angular momentum. So angular momentum at these two specified locations, or at any location, is actually remains the same. Whether it is at A, B, C, or any other location, angular momentum remains the same. So angular momentum at point A must be the same as the angular momentum at point B. This is a concept. Therefore, let's apply and try to solve for it. So the angular momentum at point A must be the same as the angular momentum at point B. There is no external torque actually exerted on it. Therefore, L, or angular momentum at point A and angular momentum at point B, remains the same. And mass, okay, mass at point A, the velocity at point A, the radius at point A must be the same as that of mass at point B, velocity at point B, and radius r at point B. The mass of the planet remains constant. From the law of conservation of mass, the mass remains constant wherever it moves. So mass of the planet remains the same, so that we can eliminate or cancel since they are equal. So we can cancel this. The velocity of the planet at point A, or at location A times radius A is equals to the velocity of the planet at point B times radius B. Therefore, we have a relation that the radius of the planet at point B, at location B, is 8 times the radius at point A. So you can substitute here as RA is equals to the velocity at point B. Instead of the RB, it's possible to have 8 times RA. 8 times RA. So we can cancel out RA by RA. So the velocity at point B is equals to the velocity at point A over 8. This is how we determine the velocity of the planet at location B. Therefore, the velocity of the planet at location B is equals to the velocity of the planet at point A is already given to be 60,000. The velocity of the planet is 60,000 meter per second. So 16,000 over 8. So when you divide this, we have 7,500 meter per second. So this is how we solve this equation. Let's try to see it back again. So here we have the alternatives. Actually, we have found it to be 7,500 meter per second. 5,700 meter per second. So I hope you have found the answer. Now let's proceed and try to add one more. Look here. Suppose here you have 5 kilogram particle moves in the xy plane with a velocity v 4.2 in the I, minus 3.6 in the j, meter per second. So what is its angular momentum? When its position vector is given to be 1.5 in I plus 2.2 in the j. So this is actually represented using vector form, vectorially. What are given quantities? The velocity is given to be 4.2 in the I, 3.6 in the j. The velocity is given to be 4.2 in the I, okay, minus 3.6 in the j. This is the velocity given. And we have also the moment arm, 1.5 in I plus 2.2 in the j. This is the moment arm. And we have a mass here. 5 kilogram particle moves in the xy plane. Therefore, we are asked to find the angular momentum. So let's try to solve it together again. The mass is given to be 5 kilogram. So how do we solve this? Well, we are asked to find the angular momentum. And angular momentum is given vectorially as the momentum cross the linear momentum. Okay, and the linear momentum can be expressed as R cross linear momentum means mass times velocity v. Velocity v. Therefore, it's possible to have R, and you can have matrix form I, J, K. I, J, K. Always you have to put R first. Here we have R. What are the coefficients of R? 1.5 to 0.2 here. So 1.5 to 0.2, and there is no K value. Okay. How about the speed or the momentum? It's possible to multiply this by 5 actually. Therefore, it's possible to have 5. Okay, 5 as a whole. Then put the velocity 4.2 in the I minus 3.6 in the J. There is no K value actually. There is no K value. Therefore, I hope you've learned about how to solve the matrix concept in your vector form. This is the answer. So I hope you have enjoyed these concepts, and I will give you this problem and try to solve it at your home. Therefore, this is all I've got for today. So see you.